The temperature dropped below freezing weeks ago and has not recovered since. Every pond for miles has sealed itself beneath a lid of ice thick enough to walk across. The birds that could leave, left. The animals that could dig deep enough to escape the cold buried themselves well below the frost line, hearts slowed, barely burning any energy at all, and waited. One creature did not dig deep enough to escape anything. Snow has owned this forest for 3 months. It has buried the fallen logs, sealed the streams, and pressed the world into a silence so complete that even the wind seems to move carefully through it. Beneath one log, tucked into a bed of dead leaves, something small lies absolutely still. Look closely and you'll see the frost. It threads through the skin like veins of glass, spreading from the surface inward. The eyes have clouded to the color of frozen milk. If you lifted this animal into your palm right now, it would not feel like a living thing. It would feel like a stone that used to be alive, hard, brittle, and cold enough to sting your skin. Its heart is not beating. Not slowing. Not faint. Stopped. No breath moves through its lungs. No electricity fires across its brain. By almost every definition medicine has ever used to separate the living from the dead, this wood frog has already crossed that line. And yet, in 8 or 9 weeks, when the sun finally breaks the ice on the pond nearby, this same frog will blink, draw its first breath in 2 months, and hop away across the thawing leaves as though nothing at all had happened. This is not resurrection. It is engineering. Weeks before the first hard freeze, the frog's liver begins flooding its bloodstream with glucose, the same sugar that fuels every cell in your own body, repurposed here for something your body could never survive. As ice begins forming between its cells, that sugar packs itself around the machinery inside each one, cushioning it from the crystals trying to tear it apart. Ice is allowed to claim everything on the outside. Life simply retreats further in, and waits. Up to 60% of the water in this frog's body will turn to solid ice. Its heart stops. Its blood stops moving. Its brain goes dark. And there it will stay, through blizzards, through nights cold enough to crack stone, suspended somewhere between the two states we've always assumed were opposites. Then, cell by cell, organ by organ, the thaw arrives, and the frog reboots itself from the inside out. If a creature this small can rewrite the line between life and death using nothing but sugar and time, what else has this planet quietly figured out that we've simply never stopped to look at? Because this frog is not a curiosity. It is an introduction. Every species alive today is a surviving answer to the same impossible question Earth has been asking since its first oceans cooled enough to hold anything alive at all: how do you keep existing, when existence itself keeps trying to stop you? Cold tries to stop you. Heat tries to stop you. Hunger tries. Darkness tries. Distance, silence, and time all try. And scattered across every ocean trench, every desert dune, every rainforest canopy and Arctic ice shelf, life has produced its own particular answer to that question, each one stranger, and more precise, than anything a writer could have invented. Off the coast of Indonesia, a soft-bodied animal with no bones and no shell flattens itself against the sand. In under 3 seconds, it becomes a flatfish. Then a lionfish. Then something banded and sinuous that swims like a venomous sea snake, because for a moment, that's exactly what it wants a predator to believe it is. Thousands of kilometers away, on the grasslands of Kenya, an elephant lifts her trunk and goes still. She has heard nothing. But somewhere beneath her feet, through solid ground, a message has just arrived, sent by another elephant kilometers away, in a language pitched too low for any human ear to register. High above a quarry in Wales, a bird folds its wings against its body and drops out of the sky, accelerating past 240 miles an hour, faster than a Formula One car reaches top speed, toward a target with almost no chance of ever seeing it coming. Off the coast of Sri Lanka, a sperm whale dives more than 2 kilometers straight down into total darkness, hunting entirely by sound, in a world sunlight has never once touched. In a fir forest in central Mexico, a single tree disappears beneath so many monarch butterflies that its branches audibly creak and bend under a weight made entirely of wings. And in an aquarium tank in New Zealand, a soft, boneless creature the size of a rugby ball waits for the lights to go out, slips through a gap barely wider than its own eyeball, crosses several meters of open floor, and vanishes down a drainpipe leading back to the sea. None of this is science fiction. Every second of it has been filmed, measured, and documented by scientists, some of whom, in more than one case, still aren't entirely sure how it's possible. Over the next 90 minutes, this journey moves from frozen forests to burning deserts, from the tallest canopy in the rainforest to the darkest trench in the ocean. You'll meet architects whose structures are visible from space, parents who give everything they have and then some, hunters so precise that evolution has had almost nothing left to improve, and alliances between species that share no common language, and yet somehow, cooperate anyway. Every scene you're about to see is real. The only thing fictional here is the idea that any of it should be possible. It begins, as most true stories of survival do, with the most basic question of all: how do you stay alive somewhere that seems built to make sure you don't? If freezing solid and returning to life sounds like the most extreme trick evolution has ever pulled, consider what's happening in the middle of the Sahara Desert at exactly noon. The sand here has reached temperatures hot enough to cook meat on contact. Every sensible creature for miles has already retreated underground, into burrows several degrees cooler, to wait out the worst of the day. Every creature except one. Silver ants surface in a narrow window when the desert is at its most lethal, and here is why: it's the only time their most dangerous predator, a lizard that cannot tolerate quite as much heat as they can, is forced to stay hidden. For a few unbearable minutes, the most dangerous place on Earth becomes, briefly, the safest place to be. The ants pay an extraordinary price to earn that window. Their bodies are covered in specialized hairs, triangular in cross-section, that reflect sunlight like tiny prisms and keep their internal temperature just low enough to function while the sand around them scorches. They run faster, relative to their size, than almost any animal on the planet, covering the ground in a blur to spend as little time as possible exposed. Some individuals still die of heat exhaustion mid-run. The colony sends them out anyway, because the alternative, waiting underground for a cooler hour, means competing with every other predator on the surface for the same shrinking scraps of food. Here, extreme risk is the strategy. Travel south, to the coldest water on the planet, and survival demands the opposite solution entirely. In the seas around Antarctica, a family of fish has done something no other vertebrate on Earth has managed: they have abandoned red blood almost completely. Icefish blood runs nearly clear, stripped of the hemoglobin every other fish, bird, and mammal relies on to carry oxygen. In warmer water, this would be a death sentence. But the water here is so cold, and holds so much dissolved oxygen, that ice fish can absorb what they need directly through their skin and thin-walled blood vessels, no red blood cells required. Their hearts, as a result, have grown enormous compared to any other fish their size, engines built to move a strange, nearly colorless blood through a body evolution decided didn't need to look like anyone else's. And if you want to see survival taken to its most literal extreme, you don't need a desert or an ocean at all. You need a microscope. Tardigrades are barely visible to the naked eye, plump, 8-legged, and about as intimidating as a grain of rice. In 2007, scientists strapped a colony of them to the outside of a satellite and launched them into the vacuum of space. No air. No pressure. Direct, unfiltered solar radiation strong enough to shred the DNA of nearly anything alive. Some of the tardigrades survived. Not just the trip. Afterward, back on Earth, several of them went on to reproduce normally. Their trick isn't strength. It's surrender. When conditions turn lethal, a tardigrade can pull nearly all the water out of its own body, curl into a dried husk called a ton, and drop its metabolism to a level so close to zero that it becomes almost impossible to call it alive in any active sense. It waits. It has been known to wait like this for years. And when water finally returns, it simply rehydrates and continues, as if the years, or the vacuum of space, had never happened at all. There's a fourth kind of survival worth pausing on, not a survival of extremes, but a survival of impossibly small margins. In a single limestone cavern in the Mojave Desert, in a pool no larger than a modest living room, lives a fish found nowhere else on the planet. The Devil's Hole pupfish has survived in this one flooded cave for thousands of years, through droughts and climate shifts, in water that never drops below 90 degrees Fahrenheit and holds barely enough oxygen to support life at all. Its entire global population, at times, has numbered only in the dozens. One algae bloom, one dropped limestone shelf, could end the species entirely, in an afternoon. And yet it persists, not through armor, or speed, or any dramatic adaptation, but simply by demanding almost nothing from an environment that offers almost nothing to give. Some species survive by outrunning death. Some by outweighting it, frozen or dried into something that isn't quite living and isn't quite gone. And some simply need so little from the world that death can find almost nothing left to take. But staying alive alone was never going to be enough. Evolution needed something else, a way for a creature that survives to warn another creature, kilometers away, about the very same danger. It needed a language. In the grasslands of Amboseli, Kenya, a herd of elephants stops walking at exactly the same moment. There was no trumpet call. No visible signal passed between them. To every human observer standing nearby, the savanna is silent. But the elephants heard something. Moments earlier, a rumbling call was produced in the throat of another elephant, kilometers away, a sound so low in frequency that it falls below the range of human hearing entirely. The sound doesn't just travel through the air. It travels through the ground itself, and elephants read it the way you might read a vibration through a table, through sensitive nerve endings in their feet and trunks, tuned to detect these ultra-low frequencies as clearly as a spoken word. An elephant family can coordinate across a landscape the size of a small country, warning of predators, announcing the location of water, or simply confirming that everyone is still safe, all in a language built entirely out of frequencies we spent most of human history not knowing existed. They are not the only ones broadcasting messages we've had to learn to hear. Inside a beehive, in complete darkness, a single forager returns from a flower patch and begins to dance. She moves in a tight figure eight, vibrating her body during the straight run through the middle of the pattern. The angle of that straight run, measured against gravity, tells every bee watching exactly which direction to fly relative to the sun. The duration of the vibration tells them precisely how far to go. Carl von Frisch spent decades decoding this dance before finally proving what it was, not instinct expressing itself as movement, but an actual transfer of information, choreographed into muscle and wing beat. He won a Nobel Prize for the discovery. The bees had been doing it for tens of millions of years before anyone thought to ask what the dancing meant. Beneath the forest floor, an entirely different kind of network may be carrying messages of its own. Threads of fungus, thinner than a human hair, weave themselves into the root systems of trees across an entire forest, forming connections some researchers have nicknamed the Wood Wide Web. Through this shared fungal network, trees appear able to exchange nutrients, a large, sun-drenched tree effectively subsidizing a struggling seedling in the shade below it. Some studies have even suggested that a tree under insect attack can trigger changes in its neighbor's chemistry before the insects ever reach them, as though a warning had passed hand to hand, root to root. How much of this constitutes deliberate communication, and how much is simply water and nutrients moving passively along the path of least resistance, remains a genuine, unresolved argument inside plant science today. But even the most cautious researchers agree on this much: a forest is not simply a collection of individual trees competing side by side. It behaves, at some level, like a single connected system. Off the coast of Australia, that same idea plays out on a far larger scale, and at a far larger volume. A male humpback whale sings a specific pattern of moans, cries, and rising calls, sometimes repeating the same complex song for 20 minutes at a stretch, for hours at a time, for an entire breeding season. And that song is not fixed. Researchers tracking whale populations across the Pacific have documented entire songs sweeping from one population to another over the course of a few breeding seasons, a new phrase appearing off the eastern coast of Australia, and showing up, note for note, in the songs of whales thousands of kilometers away in French Polynesia the following year. No one taught them the new version. It simply spread, the way a piece of music might spread from one radio station to the next, except the radio stations are separated by an ocean. And in the prairie grasslands of North America, one biologist has spent decades arguing that a rodent most people dismiss as background scenery might possess one of the most sophisticated alarm systems ever documented outside of human language. Prairie dogs issue distinct alarm calls for different predators, one call for a hawk, another for a coyote, another for a domestic dog. According to research led by Kon Slobodchikov, those calls may encode even finer detail, the approximate size, shape, speed, and even color of the specific predator involved, changing the call based on what's actually approaching. Not every scientist agrees on how much detail is truly encoded, or whether language is the right word for it at all. But few dispute this: whatever is happening in that call, it's more specific, and more deliberate, than a simple cry of alarm. None of these animals share a spoken word with us, or with each other. And yet across sound too low to hear, movement too small to notice, chemistry too subtle to detect, and threads too thin to see, this planet has been having a conversation the entire time. The only thing that changed is that we finally started listening. But hearing a message is one thing. Understanding it, solving it, turning it into a plan, requires something else entirely. It requires a mind. In 2016, staff at a public aquarium in New Zealand arrived one morning to find a tank standing empty. Its resident, a common octopus named Inky, had waited until the building was dark and quiet. He had squeezed his entire boneless body. Every octopus can compress itself through any gap larger than its beak, the only hard part of its anatomy, through a small gap at the top of his tank. He had crossed several meters of aquarium floor. And he had found, and entered, a drain pipe leading directly back to the ocean. No one taught him this. No one had shown him a map. He simply assessed his situation, identified an opportunity, and executed an escape plan good enough that human engineers would recognize it as one. This is not an isolated anecdote. It's a symptom of something extraordinary happening inside an animal whose last common ancestor with us lived over 500 million years ago, long before anything resembling a backbone existed on this planet. An octopus has roughly the same number of neurons as a dog, but 2/3 of those neurons live not in its brain, but distributed through its 8 arms. Each arm can taste what it touches, process information, and in some documented cases, react to stimuli even after being separated from the rest of the body. It isn't quite accurate to say an octopus thinks with one mind. It may be closer to the truth to say it thinks with 9, in constant negotiation with each other. In laboratory tests, octopuses have opened child-proof jars from the inside to retrieve food. They've learned to navigate mazes, recognized individual human faces well enough to target specific researchers with jets of water, and shown clear signs of play, manipulating objects with no food reward at all, seemingly for the simple experience of it. They are not alone in this kind of mind. On the Pacific island of New Caledonia, a species of crow does something that, until recently, scientists assumed was reserved for humans and a small handful of great apes. It manufactures tools, to a design, for a specific purpose it hasn't encountered yet. New Caledonian crows strip barbs from leaves to create hooks capable of extracting grubs from deep crevices in dead wood, and they don't just use one design. Different populations of crows on different parts of the island have developed different tool shapes, passed down and refined across generations, the way a craft tradition might evolve regionally over centuries. In laboratory testing, these same crows have solved an ancient fable in real time. Presented with a container of water too low for them to reach a floating piece of food, they select and drop stones into the container, raising the water level, until the food comes within reach. Aesop wrote a version of this exact puzzle over 2,000 years ago as a fable about cleverness. The crows solve it as a Tuesday. In the warm waters of Shark Bay, Australia, a population of bottlenose dolphins has developed something even stranger, a regional tool use tradition, passed almost exclusively from mother to daughter. These dolphins tear marine sponges from the seafloor and wear them over their snouts like a glove, using the sponge to protect themselves from sharp rocks and stinging creatures while foraging for fish hidden in the rubble below. No other dolphin population on Earth does this. It isn't instinct. It's culture, a specific, learned behavior invented at some point by a single individual, and carried forward ever since through the one relationship every dolphin trusts completely. Dolphins also appear to give each other names. Each dolphin develops a unique signature whistle early in life. Other dolphins learn to recognize and even mimic that whistle specifically to get that individual's attention, calling out, in effect, across open water, to a particular someone. In 2012, a group of leading neuroscientists gathered at the University of Cambridge and signed a document that would have been considered radical a generation earlier. The Cambridge Declaration on Consciousness stated, based on the accumulated weight of evidence, that the neurological structures required for conscious experience are not uniquely human, that they exist across all mammals, all birds, and in at least some other creatures, explicitly naming octopuses among them. None of this proves that an octopus dreams the way you do, or that a crow reflects on its own cleverness the way a person might. But it does mean the old, comfortable line, the one separating instinctive animals from a single conscious species standing apart from them, has become far harder to draw than anyone assumed a few decades ago. Intelligence, though, doesn't exist in a vacuum. In the wild, a mind is only as valuable as what it can accomplish in the seconds that matter most. And nowhere do those seconds matter more than in the moment life and death collide, at full speed, with absolutely no time left to think at all. "9,000 feet above a quarry in Wales, a bird tucks its wings against its body and simply stops flying. It falls instead, and then it accelerates. Within seconds, a peregrine falcon in a hunting stoop has been measured exceeding 240 miles an hour, faster than a Formula One car reaches top speed, faster than anything else on the planet with a pulse. Small conical structures inside its nostrils break up the rushing air so the bird can still breathe at that speed without its lungs collapsing under the pressure. A specialized third eyelid sweeps across each eye like a windshield wiper, clearing debris without ever slowing the fall. At the final possible instant, the falcon extends its talons, strikes its target with the force of a small missile, and the hunt is often over before the prey has finished registering that anything was wrong. Evolution has spent tens of millions of years refining this single maneuver. There is remarkably little left to improve. Off the icy coast of Antarctica, an entirely different kind of perfection plays out, not the perfection of a single body, but the perfection of a plan, executed by many. A pod of orcas spots a seal resting on a drifting ice floe, apparently safe, surrounded on all sides by open water. The whales begin swimming in tight formation, directly at the floe. At the last possible moment, they dive in unison, generating a single coordinated wave that washes clean over the ice, breaking it apart and sweeping the seal into the water among them. This is not a lucky accident of ocean currents. It is a rehearsed, deliberate hunting technique, taught by older whales to younger ones across generations, adjusted in real time to the size of the floe and the position of the prey. In the shallow waters off Argentina and the subantarctic Crozet Islands, some orca populations take this cooperation a step further, intentionally beaching themselves at speed to snatch sea lion pups directly off the sand, then thrashing themselves back into the surf before the tide can strand them for good. It is one of the most dangerous hunting techniques ever documented in a marine mammal, refined and passed down within specific family lines, and almost never attempted by orcas outside those same lineages. This isn't only instinct. It is inherited expertise. Not every perfect hunter needs speed, or teamwork, or open water at all. Beneath the desert floor, a trapdoor spider builds a burrow sealed with a camouflaged lid made of silk, soil, and vegetation, indistinguishable from the ground around it. Then it waits, sometimes for days, with its front legs resting lightly against silk trip lines radiating out from the entrance like the spokes of a wheel. The instant an insect's footstep disturbs one of those threads, the spider bursts through its own front door in a fraction of a second, seizes its prey, and vanishes back underground before most cameras can even resolve the motion into a clear image. And in the coral reefs of the Indo-Pacific, one of the strangest weapons in the animal kingdom belongs to a creature barely the length of your hand. The peacock mantis shrimp strikes with a specialized club-shaped appendage that accelerates faster than a fired bullet leaves the barrel of a gun, generating so much force underwater that it creates a cavitation bubble, a pocket of collapsing vacuum that produces a second, nearly simultaneous shockwave, along with a flash of light and heat too brief for the naked eye to register. The strike itself can shatter the shell of a crab, or the glass of an aquarium tank not built to contain it. To track all of this, the mantis shrimp relies on what may be the most elaborate visual system in the natural world, up to 16 different types of photoreceptors, compared to the 3 most humans possess, capable of detecting forms of light, including polarized light, that the rest of us cannot perceive at all. Every one of these hunters represents millions of years spent perfecting a single, narrow task, converting opportunity into a kill with as little wasted motion, and as little wasted time, as biology will allow. But perfection cuts both ways. For every hunter this precise, evolution built something equally precise on the other side of the encounter, because if you cannot outrun a falcon, outswim an orca, or outfight a mantis shrimp, there is exactly one option left. You disappear. A cuttlefish drifting over a reef in the coral triangle changes the entire pattern of its skin in under a second, mottled browns shifting into bands, spots blooming and fading, ridges rising out of smooth skin to mimic the exact texture of the coral rubble below it. This alone would be remarkable. What makes it almost unbelievable is this: cuttlefish are colorblind. Every test devised to check for color vision in their eyes has come back the same way. They shouldn't be able to perceive the colors they're matching so precisely. Some researchers now suspect cuttlefish may be sensing light directly through photoreceptor proteins embedded in their own skin, effectively seeing color with their entire body instead of only their eyes. No one has fully solved this puzzle yet. It remains, genuinely, an open question in modern science. A short swim away, a relative of the cuttlefish takes disguise even further, into outright performance. The mimic octopus doesn't simply blend into its surroundings. It impersonates other animals entirely, flattening its body and undulating along the seafloor to imitate a venomous flatfish, or trailing its arms behind it to mimic the banded pattern and swimming motion of a poisonous sea snake, or spreading its arms wide and raising ridges along its skin to imitate the spines of a lionfish. Researchers have documented it convincingly impersonating well over a dozen different species, apparently selecting which impression to perform based on which specific predator is threatening it at that moment, a soft-bodied animal with no bones and no shell, defending itself by pretending, convincingly, to be something else entirely. On the forest floor of Southeast Asia, an insect has taken the opposite approach. Instead of imitating a threat, it imitates something harmless enough that its prey never bothers to be afraid at all. The orchid mantis has evolved pale petal tone coloring and broadened, leaf-like lobes along its legs, arranging its body into a shape close enough to a flower that pollinating insects will sometimes land directly on it, mistaking a predator for a place to feed. Exactly how much of this resemblance evolved specifically to lure pollinators, and how much is simply effective camouflage against a genuinely flower-covered background, remains debated among the scientists who study it. What isn't in question is the result: an ambush predator patient enough, and convincing enough, to let its next meal walk directly into range. Elsewhere in the same forests, entire lineages of insects have committed so completely to disguise that camouflage has become their entire way of life. Stick insects and leaf insects have evolved bodies indistinguishable from twigs and foliage, veined patterns that mimic leaf damage, edges that curl like something browning at the tips, even a gentle side-to-side sway while walking, echoing the movement of a leaf caught in a light breeze. And far above the ground, one predator has turned disguise into a hunting weapon rather than a defense. The zone-tailed hawk shares its silhouette, its wingspan, and even its lazy, tilting flight pattern with an animal most prey species have learned to completely ignore, the turkey vulture, a carrion-eating bird with no interest in live prey at all. Zone-tailed hawks will often fly directly within loose flocks of vultures, adopting their unhurried circling pattern, lulling potential prey below into treating the entire group as harmless scavengers. Then, at the moment of opportunity, the hawk peels away from the formation and strikes, a predator that spent its entire approach disguised as something its victim had already decided wasn't worth fearing. Camouflage, mimicry, disguise, three different names for the same underlying strategy, deployed by creatures that share almost nothing else in common. But not every species chose to specialize in vanishing. Some chose, instead, to build something so large, so permanent, and so deliberately engineered that hiding was never the point at all. From above, the mound rises nearly 4 meters out of the Australian outback floor, taller than a 2-story house, built entirely from mud, saliva, and the compacted droppings of the millions of termites living inside it. The structure itself is a marvel of passive engineering. As the sun heats the mound through the day and the surrounding air cools it at night, temperature differences drive air to circulate through an internal network of tunnels and chambers, drawing stale air up and out while pulling fresh air in from below. Scientists once described this as something close to natural air conditioning. More recent research has refined that picture. The mound behaves less like a machine holding a fixed setting, and more like a lung, expanding and contracting its airflow across each daily heating and cooling cycle to keep the colony within a survivable range, even as outside temperatures swing by tens of degrees. Some termite species, known as compass termites, go a step further, building their entire mound as a thin, wedge-shaped blade oriented precisely north to south. The narrow edge faces the punishing midday sun, minimizing direct exposure, while the broad flat sides catch the gentler light of morning and evening. Termites are not the only engineers reshaping their environment on a scale you can see from space. In northern Canada's Wood Buffalo National Park, satellite imagery revealed, in 2007, a single beaver dam stretching more than 800 meters across a stretch of wetland, long enough to be seen clearly from orbit, believed to represent the combined work of multiple generations of the same beaver family. A dam like this doesn't simply provide shelter. It reshapes an entire watershed, converting flowing streams into slow, still ponds, creating wetland habitat that dozens of other species depend on entirely. Few animals on Earth reshaped their environment this dramatically. For most of history, humans assumed we were the only one. Elsewhere, architecture serves a purpose that has nothing to do with shelter, and everything to do with courtship. A male weaverbird builds an elaborate, tightly woven nest from grass and reeds, knotting and threading each strand with a precision that looks almost mechanical. When he finishes, he performs beneath it, wings fluttering, calling out to attract the female's attention to his work. And if she inspects the nest and finds it lacking, too loose, too asymmetrical, poorly ventilated, she will simply leave. The male doesn't argue. He tears the entire nest apart and starts again, sometimes several times over, until either his craftsmanship improves or his patience runs out. And in warm, shallow waters around the world, colonies of a soft-bodied animal barely larger than a pinhead have built something more massive than any construction project in human history, reef systems that form the largest living structures on the planet, some large enough to be visible from orbit. Each individual coral polyp secretes a small skeleton of calcium carbonate, and dies, and is built over by the next generation, layer upon layer, for centuries, sometimes millennia. Inside their tissue lives a microscopic algae, providing the coral with the majority of its energy through photosynthesis in exchange for shelter and access to sunlight, a partnership so essential that when ocean temperatures rise and the algae are expelled in a stress response we call bleaching, the coral itself frequently starves and dies within weeks. Ventilation systems tuned to a desert sun. Dams visible from space. Nests inspected and rejected like a job application. Skeletons built one generation at a time into the largest living structures on Earth. None of it happens quickly. But even the most permanent structure in nature is only useful if its builder is still alive to reach it, and for many species, reaching home again is the single hardest task they will ever attempt. In October of 2022, a young bar-tailed godwit, barely 5 months old, lifted off from the mudflats of southwestern Alaska and did not land again for 11 straight days. It flew through storms. It flew through open ocean with no island, no ship, and no shoreline in sight for thousands of kilometers. It burned through fat reserves built up over the preceding weeks, along with muscle from its own digestive organs, which shrink during the flight since there's nothing to digest and no room for anything not essential to staying airborne. By the time it finally touched down in Tasmania, satellite trackers confirmed it had flown more than 13,000 kilometers, without a single stop to rest, drink, or feed, the longest non-stop flight ever recorded for any bird, and quite possibly for any animal on Earth. It had never made this journey before. No parent flew beside it to show the way. Adult godwits leave the breeding grounds first, and juveniles complete this exact route entirely alone, guided by some combination of an internal magnetic compass, a memory of the sun's position, and instructions apparently written into its biology before it ever hatched. Few migrations rival that single flight for endurance. But one bird may rival it for sheer distance covered across an entire lifetime. The Arctic tern breeds in the high Arctic each summer and then, rather than settling in for the winter, flies to the opposite end of the planet, spending the northern winter in the waters around Antarctica before returning north again the following spring. Researchers who have tracked individual terns with tiny geolocators have recorded round-trip distances exceeding 70,000 kilometers in a single year, often along zigzagging routes that chase favorable winds rather than traveling in a straight line at all. Across an average lifespan of roughly 30 years, the accumulated distance is often described as the equivalent of multiple round trips to the moon. And because it chases summer at both ends of the Earth, a single Arctic tern experiences more hours of daylight over the course of its life than any other creature alive. Not every migration is measured in the distance one individual travels. Some are measured in what a species accomplishes across multiple generations, none of which ever complete the journey themselves. Each autumn, monarch butterflies across the eastern half of North America begin flying south, converging with uncanny precision on the same small cluster of Oyamel fir forests in central Mexico, often the very same trees their ancestors overwintered in the year before. This alone would be unremarkable, except for one detail: the butterflies making this journey have never been to Mexico. Multiple short-lived generations are born and die across the summer, each one migrating a little further north, until finally, a special, super generation, emerges in early autumn, biologically built to live many times longer than its parents, purely so it can complete a flight of thousands of kilometers to a forest it has never seen. How, precisely, that information passes down without ever being demonstrated firsthand remains one of the open questions researchers are still working to fully answer. On the plains of East Africa, migration takes on a different character altogether, not a single individual, and not a single species, but nearly 2 million wildebeest, zebra, and gazelle, moving together in a rough, sprawling circuit that follows the rain. The herd doesn't travel by a fixed calendar. It travels by scent and cloud cover, sensing distant rainfall and the fresh grass that follows it, sometimes changing direction with little warning. At several points along the route, the only way forward crosses a river thick with crocodiles waiting exactly for this moment, every year, without fail. Some animals will not make it across. The vast majority will, and the herd will keep moving, because standing still, on these plains, is its own kind of danger. And beneath the ocean's surface, one of the most quietly astonishing migrations of all takes place inside the mind of a single hatchling. A newborn sea turtle, minutes old, crawls down a beach and swims directly out into open ocean, where it will spend years, sometimes decades, traveling enormous circuits across entire ocean basins. And when the time finally comes to nest, an adult female will frequently return to the exact same stretch of coastline where she herself hatched, sometimes the very same beach, after years spent roaming thousands of kilometers of open water. Researchers believe she accomplishes this using a kind of internal map, imprinted in the earliest minutes of her life, built from the unique magnetic signature of that one particular coastline. None of these animals are traveling for the sake of the journey. Every mile, every storm survived, every river crossing, exists to serve one single biological purpose, to arrive somewhere safe enough, and stay alive long enough, to become a parent. And in nature, that role, the role of a parent, is very rarely free. Deep in a rocky crevice off the coast of California, a female octopus has not eaten in weeks. She laid her eggs months earlier, as many as 100,000 of them, strung in delicate chains from the roof of her den, and since that moment, she has not left them. Not to hunt. Not to feed. She spends her days gently blowing currents of water across the eggs with her siphon, keeping them oxygenated, and using the suckers along her arms to clean away algae and parasites, over and over, without pause. As the weeks pass, her body begins visibly failing. She grows pale. Her skin, once capable of camouflage sophisticated enough to fool a predator at a glance, begins to lose its ability to change color at all. She is, quite literally, starving to death in real time, in full view of anyone watching. For a long time, scientists assumed this was simply an unfortunate side effect of neglecting to eat. Research published in 2018 found something far stranger happening beneath the surface. A small organ near her eyes, called the optic gland, begins flooding her body with a cascade of hormonal changes after she lays her eggs, changes that don't just cause her body to break down, but appear to actively drive her toward it, shutting down her feeding behavior and accelerating her own decline. It is not an accident of exhaustion. It is closer to a switch, built into her biology, that flips the moment her eggs are laid. In nearly every observed case, she dies within days of her eggs finally hatching, her very last act as a mother. Thousands of kilometers south, in the depths of Antarctic winter, an entirely different parent is making a different kind of sacrifice, one measured not in death, but in almost unimaginable endurance. After a female emperor penguin lays her single egg, She transfers it with extraordinary care onto her mate's feet, where he tucks it beneath a warm fold of skin and feather, and then she leaves, traveling on foot for days back to open water to feed, rebuilding the reserve she spent producing that one egg. The male stays behind. For the next 2 months, through the coldest, darkest season on the surface of the planet, with temperatures plunging below -60°C and winds strong enough to strip the skin from exposed flesh, he does not eat. He barely moves, huddling together with thousands of other males in a slow-rotating formation, each bird taking its turn at the punishing outer edge of the group before shuffling back toward the shielded center, so that no single penguin bears the worst of the wind for too long. He loses nearly half his body weight. And still, he protects that single egg, without fail, until his mate finally returns, by which point, in many cases, he has gone without food for well over 100 days. Not every sacrifice in the animal kingdom ends when the offspring survives, either. For some species, the bond appears to outlast the child entirely. Researchers studying elephants across East Africa have documented, repeatedly, a behavior that resists easy explanation. Elephants encountering the bones of a dead elephant, even one unrelated to them, even years after death, will often stop. They will approach slowly, and use their trunks to touch and turn the bones over, again and again, with what looks, to any human observer, like unmistakable care. Mothers who have lost a calf have been documented remaining near the body for days, occasionally attempting to lift it, reluctant to leave even long after any chance of the calf reviving has passed. Scientists are careful, and rightly so, about assigning human emotional language to animal behavior we can only observe from the outside. But few researchers who have spent real time in the field studying elephants are willing to call this behavior nothing at all. Sacrifice, across the natural world, rarely looks sentimental. It looks, instead, like biology quietly keeping score, a mother's body breaking down exactly on schedule, a father's fat reserves burning exactly fast enough to last exactly as long as needed, a species' entire genetic strategy rearranged around the simple fact that some individuals matter more to the future than others. And yet none of that makes it any less remarkable to witness. An octopus dying the instant her final purpose is fulfilled. A father standing motionless through the worst weather on the planet, protecting something the size of a large egg, for months, without complaint, because complaint was never an option his biology gave him. Call it instinct if you prefer the safer word. But watch enough of it happen, in enough different species, across enough different corners of this planet, and you may find the word love becoming difficult to fully avoid. Not every bond in nature, though, is built between a parent and a child. Some of the deepest partnerships on Earth exist between species that share no blood relation at all, creatures with nothing biologically in common, who have nonetheless learned that they need each other to survive. A clownfish glides between the swaying, venomous tentacles of a sea anemone, brushing against them again and again, apparently without consequence. For almost any other fish, this would be a fatal mistake. Anemone tentacles are lined with microscopic stinging cells, triggered by touch, capable of paralyzing prey many times the anemone's own size. But the clownfish is coated in a specialized layer of mucus that the anemone's stinging cells fail to recognize as a threat, allowing the fish to live directly among the one predator almost nothing else in the reef dares to approach. In exchange for that extraordinary shelter, the clownfish doesn't simply hide and take. It aggressively defends its host anemone from other species that would otherwise eat its tentacles, circulates water through the anemone with its constant movement, and contributes nutrients through its own waste. Neither species could easily achieve on its own what they accomplish together. Not every partnership in nature is this equal, and some that look cooperative on the surface turn out to be far more complicated underneath. For decades, the relationship between oxpeckers and large grazing mammals like rhinos and buffalo was presented as a textbook example of perfect mutual benefit. The bird removes ticks and parasites from the mammal's skin, gets a free meal, and the mammal gets pest control, at no cost to either side. More recent research has complicated that tidy picture considerably. Oxpeckers have been observed deliberately keeping wounds open on their host skin, feeding on blood rather than parasites, behaving less like a groomer and more like a small, tolerated parasite themselves. The relationship isn't a lie, exactly. It's simply messier than the story first suggested, closer to an uneasy, situational truce than a clean partnership. Elsewhere on the reef, an even stranger kind of truce plays out in plain sight, dozens of times a day. At what marine biologists call cleaning stations, small cleaner fish and cleaner shrimp set up shop along a particular patch of coral, and larger fish, including predators easily capable of swallowing the cleaners whole, line up and wait their turn. A grouper will hover motionless, mouth open, gills flared, while a cleaner wrasse swims directly inside its mouth to pick away parasites and dead tissue, and swims back out again entirely unharmed. For those few minutes, an unspoken agreement holds: predator and prey suspend the only relationship they'd otherwise have, because the service being provided is valuable enough to both sides to be worth the risk. Some alliances involve considerably more manipulation than mutual respect. Certain species of ants tend colonies of aphids the way a farmer might tend livestock, protecting them from predators, and in some cases physically carrying aphids to new plants when a food source runs low, purely to preserve access to the honeydew the aphids secrete as a byproduct of feeding. In return, the aphids receive protection they could never provide for themselves. It's difficult to say which species is really in charge of this relationship. And in burrows along tropical seafloors, one of the most quietly touching partnerships in the ocean plays out between two animals that could not be more different from each other. A pistol shrimp, nearly blind, digs and maintains an elaborate burrow in the sand, doing virtually all of the physical labor for both residents. A goby fish moves in alongside it, contributing nothing to construction, but providing something the shrimp desperately needs: eyesight. The goby hovers just outside the burrow entrance, watching for predators, while the shrimp keeps one antenna in constant physical contact with the fish's tail. The moment the goby senses danger, it flicks that tail, and the shrimp, instantly alerted through touch alone, retreats into the burrow, often pulling the goby in right behind it. None of these species evolved with any concept of friendship, fairness, or gratitude. Every one of these alliances persists purely because, at some point in evolutionary history, cooperating turned out to work better than competing. And yet, watching a nearly blind shrimp trust its life, moment to moment, to the flick of a tail belonging to a completely different species, it becomes difficult to reduce these partnerships to arithmetic alone. Every alliance we've explored so far has occurred somewhere within reach of daylight, somewhere a camera, a diver, or a drone could eventually capture it. But the largest habitat on this planet exists almost entirely beyond any of that, a world of permanent night, crushing pressure, and creatures that had to solve an entirely different problem. How do you live, hunt, and find a mate, in a place where light itself barely exists at all? Sunlight disappears entirely by around 1,000 meters below the ocean's surface. Beyond this point lies, by volume, the single largest habitat for life anywhere on Earth, larger than every forest, desert, and grassland combined, and yet it remains one of the least explored places on the planet. Ocean scientists frequently point out an uncomfortable fact: we possess more detailed maps of the surface of the Moon and Mars than we do of the floor of our own ocean. Into this permanent night, evolution introduced light of its own making. The vast majority of animals living in the deep sea produce their own bioluminescence, generating light through chemical reactions inside their own bodies, for purposes ranging from hunting to mating to pure self-defense. Some species use flashes of light to startle a predator mid-attack. Others eject a glowing cloud of bioluminescent mucus or ink, leaving a brightly lit decoy behind while the animal itself vanishes into the dark in the opposite direction. Few creatures illustrate this stranger side of survival better than the anglerfish. A female deep-sea anglerfish carries a bioluminescent lure extending from her head like a fishing rod, glowing not from her own tissue directly, but from colonies of light-producing bacteria she houses specifically for this purpose. In the total darkness of the deep sea, that single point of light is often the only visible object for meters in every direction, drawing curious prey close enough for her enormous, backward-curving teeth to make sure they never leave. Male anglerfish, in many of these same species, take an entirely different evolutionary path. Dramatically smaller than the females, a male will locate a female using scent, bite into her body, and over time, physically fuse to her, his own circulatory system gradually merging with hers, his independent organs withering away until he exists as little more than a permanent, attached pair of testes, guaranteeing fertilization whenever she is ready to spawn, in a lightless world where finding a new mate a second time might otherwise be close to impossible. Deeper still, in the crushing cold beyond 1,000 meters, another animal offers a clue to just how seriously deep-sea creatures take the threat lurking above them. The colossal squid possesses the largest eyes of any known animal, each one roughly the size of a dinner plate. For years, this seemed like evolutionary overkill in an environment with almost nothing to see. Researchers eventually proposed a more unsettling explanation: those enormous eyes may exist specifically to detect the faint bioluminescent disturbance created by an approaching sperm whale, the colossal squid's primary predator, from a distance great enough to matter. In waters so dark that even a whale the length of a school bus might otherwise arrive completely unseen. Other deep-sea residents have leaned even further into the strange. The vampire squid, despite its name, is neither a vampire nor technically a squid at all, but a small, dark red cephalopod uniquely suited to the near-total absence of oxygen at extreme depths. Rather than releasing ink like its shallow-water relatives, a threatened vampire squid can invert its own webbed arms entirely over its body, presenting a predator with a spiked, unfamiliar shape, while simultaneously releasing a cloud of glowing bioluminescent mucus to further confuse an attacker in the dark. Every one of these creatures represents a separate answer to the same fundamental problem: how do you hunt, hide, and reproduce in a place with no daylight, immense pressure, and almost no margin for a wasted meal? And new answers are still being discovered. Marine biologists estimate that a significant share of deep-sea species collected during recent expeditions have never been formally described or named at all, meaning that somewhere below the surface of the ocean, right now, creatures are living out entire life cycles that no scientist has ever observed. We have charted the surface of other worlds in more detail than the floor of our own. Which raises an uncomfortable question: if a habitat this close to home can still hide this much, What other rules have we assumed were fixed, simply because no one had looked closely enough to test them? One of the oldest rules of all might be next. In a laboratory tank in Mexico City, an axolotl drifts near the bottom of its enclosure, one of its front limbs freshly regrown after being lost only weeks earlier, not as a scar, not as a stump, but as a complete, functioning leg, bones, muscle, and all, indistinguishable from the one it replaced. This isn't a party trick reserved for a single limb. Axolotls can regenerate portions of their spinal cord, their heart tissue, and even parts of their own brain, healing injuries that would leave permanent, irreversible damage in almost any other vertebrate on the planet, humans included. Somehow, cells at the site of the wound seem to remember what they used to be, and what they need to become again, reorganizing themselves back into working muscle, nerve, and bone with no scarring left behind. Researchers have spent decades trying to fully decode this ability, hoping to eventually apply pieces of it to human medicine. So far, the axolotl has kept most of its secret to itself. Off the coast of Japan and the Mediterranean, a creature smaller than your fingernail may have gone even further, solving not injury, but aging itself. When a Turritopsis dohrnii jellyfish is injured, starved, or simply stressed by unfavorable conditions, it can respond by doing something no other known animal can, reversing its own development entirely, transforming its mature body back into an earlier polyp stage, essentially becoming young again from a biological standpoint, before growing back into adulthood once conditions improve. In laboratory settings, this cycle has been repeated over and over, with no observed upper limit. Researchers have started calling it, only half-jokingly, biologically immortal, not invulnerable to being eaten or killed, but seemingly without an internal expiration date written into its own cells. Beneath the deserts of East Africa, an entirely different animal has taken on aging using a stranger toolkit still. Naked mole rats live in underground colonies structured almost like an insect hive, with a single breeding queen and a supporting cast of workers, and they do something that defies almost everything we understand about mammal biology. They rarely develop cancer, they maintain stable health markers well into old age instead of gradually declining, and some individuals have been documented living past 30 years. Extraordinary for a rodent roughly the size of a mouse, species that typically survive only 2 or 3 years in the wild. Their cells appear to carry unusually effective mechanisms for repairing damaged DNA and resisting the uncontrolled growth that defines cancer in almost every other mammal studied, including us. None of these animals has defeated death outright. Axolotls can still be killed by injury or disease. Immortal jellyfish are still eaten by predators long before their reversal trick ever gets the chance to matter. Naked mole rats still eventually die, just on a timeline that shouldn't make biological sense for an animal their size. But each of them has quietly dismantled a rule we once assumed was absolute, that damage is permanent, that aging is inevitable, that every clock, once started, only ever counts down. Scientists studying all three are asking the same underlying question from different directions: is aging truly a fixed, unavoidable law of biology, the way gravity is a law of physics? Or is it simply one more evolutionary strategy among many, one that most species happen to settle on, but that a small handful of outliers, for reasons still being discovered, decided not to follow? It's tempting to imagine a future where some of these tricks transfer to us directly, a medicine built from jellyfish, or mole rats, or a salamander's stubborn cells. That future, if it ever arrives, remains a long way off, and no responsible scientist studying these animals would promise otherwise. But perhaps the value of these creatures was never only about what we might someday borrow from them. Perhaps it's simply this: on a planet where every living thing eventually loses its war against time, a jellyfish, a salamander, and a rodent the size of a mouse have each found their own small, strange way to make that war last considerably longer than it should. And somewhere in that small, strange victory lies a clue to everything else this journey has shown you, because every creature in this film, in the end, has been fighting some version of that exact same war. In the pitch-black interior of a cave in Borneo, a bat exits into open night air and instantly begins producing sound at a frequency far beyond anything a human ear could register. It is not calling out to anything. It is building a picture. Each ultrasonic pulse travels outward, bounces off every surface in its path, insect wings, cave walls, tree branches, and returns to the bat's ears as an echo, arriving at a slightly different moment and pitch depending on distance and texture. From those returning echoes alone, the bat assembles a live, three-dimensional map of a world it cannot see at all, precise enough to track and intercept a single moth twisting through open air in complete darkness. As it closes in on prey, the bat increases its call rate dramatically, sometimes to more than 100 pulses a second, a technique researchers call the terminal buzz, refining its picture of the target's position right up until the instant of contact. Beneath the sand of a shallow lagoon, a stingray lies buried and motionless, invisible to sight. A nearby shark finds it anyway. Sharks detect prey using a sense with no real human equivalent: electroreception. Jelly-filled pores clustered around a shark's snout, called the ampullae of Lorenzini, can register the faint electrical fields every living muscle generates simply by contracting, fields far too small to be seen, heard, or felt by almost anything else in the ocean. A flatfish hiding completely under sediment, invisible and scentless, still broadcasts the electrical signature of its own beating heart. To a shark, that signature might as well be a spotlight. In the warm darkness of a desert night, a rattlesnake tracks a rodent it cannot see using an entirely different kind of vision, layered directly on top of its normal eyesight. Small pit organs, positioned between each eye and nostril, contain a membrane so sensitive to infrared radiation that the snake can detect the body heat of prey from a meter or more away, day or night, effectively building a thermal image of its surroundings independent of light. Strike accuracy in complete darkness, guided by heat alone, rivals what the snake manages in daylight. High above, an entirely different, and considerably stranger, sense may be guiding an animal across an ocean it has never crossed before. Migratory songbirds appear able to detect Earth's magnetic field, and one leading explanation for how borders on the edge of quantum physics. A light-sensitive protein in the bird's eye may generate a pair of electrons whose behavior is subtly influenced by the angle of the surrounding magnetic field, a phenomenon researchers call the radical pair mechanism. If the theory holds, some migratory birds may be quite literally seeing the Earth's magnetic field as an overlay on the world in front of them, a compass built from quantum mechanics rather than a needle. The details remain a genuinely open, actively contested question in modern biophysics. And underground, in the wetlands of North America, the fastest eater ever measured among mammals relies on a sense built almost entirely out of touch. A star-nosed mole's snout ends in 22 small, fleshy tentacles, ringed with more touch receptors than an entire human hand. Foraging blind through mud and water, the mole sweeps this star-shaped organ across its path many times a second, identifying and consuming edible prey in a fraction of a second, faster than the human eye can reliably follow on ordinary video. None of these senses are better or worse than human sight, hearing, or touch. They are simply built to answer questions our own senses were never designed to ask. What does an electrical field feel like? What does the planet's magnetism look like? What does darkness feel like, mapped in exquisite, three-dimensional touch? Every one of these animals is, in effect, perceiving a version of this same planet that we will never be able to fully imagine, because we were never given the equipment to try. But perception alone has never been the whole story in nature. Wherever resources are limited, and status is contested, every one of these finely tuned senses eventually gets put to a much older, much more dangerous use. On a beach in California, two male elephant seals rear up onto their hind flippers and slam their full weight into each other, again and again, in a contest that can last the better part of an hour. Only a small fraction of males present on this beach will ever mate at all. In many elephant seal colonies, a handful of dominant males, sometimes fewer than 1 in 10, father the overwhelming majority of pups born that season. Every other male on the beach is, in evolutionary terms, largely irrelevant to the next generation, unless he can fight his way into that small circle of winners. On the plains of East Africa, competition takes a more calculated, and considerably darker, form. When a new coalition of male lions succeeds in taking over a pride, one of the first things that often follows is the death of cubs sired by the previous males. From a human perspective, the behavior is difficult to watch. From a strictly evolutionary standpoint, the logic is brutally simple. A lioness will not return to fertility while she is still nursing another male's cubs, and a new coalition of males typically holds a pride for only 2 to 3 years before being challenged and displaced in turn. Every month spent waiting for cubs that aren't his own is a month closer to losing the chance to father any cubs at all. For decades, discoveries like this one were framed as proof of an unbridgeable gap between humans and the rest of the animal kingdom. Sustained, organized, group-level violence, the story went, was something only we were capable of. Then, beginning in 1974, researchers at Gom Stream in Tanzania documented something that upended that assumption entirely. A single community of chimpanzees split into 2 rival factions, and over the following 4 years, males from the larger faction systematically tracked down members of the smaller one in a sustained pattern of coordinated, repeated violence between groups, something primatologists have since described, carefully, as resembling a war. It remains one of the most significant, and most uncomfortable, discoveries in the study of animal behavior, suggesting that at least one other species shares not just our capacity for cooperation, but our capacity for this kind of prolonged, organized conflict as well. Not every social contest ends in violence, and not every hierarchy exists purely to determine who fights whom. In the Kalahari Desert, a meerkat colony runs on a strict social structure built around a single dominant breeding female, but the colony's survival depends just as heavily on cooperation as it does on hierarchy. While most of the group forages, at least one meerkat stands sentinel duty, perched upright on its hind legs, scanning the sky and horizon for danger and calling out specific alarms for different threats, a task that pulls the sentinel away from feeding and puts it at slightly higher individual risk, purely for the group's benefit. Researchers have found that meerkats take turns at this duty, and pups are actively taught, through repeated supervised exposure, how to safely handle dangerous prey like scorpions before they're considered independent. Competition and cooperation, it turns out, were never really opposites in the natural world. They are two settings on the exact same evolutionary dial, and almost every social species alive uses both, sometimes within the same hour, depending entirely on what the moment, and the math, demands. The rarest achievement in nature isn't winning every contest. It's knowing, instinctively, which kind of contest is actually worth having. When the sun sets over a summer field in the eastern United States, thousands of fireflies begin flashing in patterns as specific, and as meaningful, as any language spoken in daylight. Each species produces its own distinct flash pattern, a particular rhythm of pulses, timed to specific intervals, that males use to advertise themselves to females scattered through the grass below. But at least one genus has turned this signal into a trap. Female fireflies of the genus Photuris have learned to mimic the courtship flash pattern of an entirely different species, luring in hopeful males expecting a mate, and eating them instead. Even in a conversation built entirely out of light, there is room for deception. Above that same field, an owl passes overhead in near total silence. Most birds in flight generate audible turbulence as air rushes across the trailing edge of each wing. Owls have evolved a soft, comb-like fringe along their primary feathers that breaks up this turbulence before it can generate sound, along with a velvety surface texture across the rest of the wing that absorbs any remaining noise. The result is flight quiet enough that a resting owl can detect the rustle of a mouse in dry grass from a considerable distance, and close the entire remaining gap without ever alerting its prey that anything is approaching, until it's already too late to matter. In the forests of the Philippines and Indonesia, a small primate called the tarsier has committed so completely to hunting after dark that its eyes have outgrown its own skull's ability to accommodate them comfortably. Each eye is larger than its entire brain, so large that a tarsier cannot rotate them within their sockets at all. Instead, evolution solved the problem differently. A tarsier can rotate its head nearly the full way around to compensate for eyes too large to move on their own. None of these animals experience the night as an absence, the way we tend to. For a firefly, it's a canvas built for signaling. For an owl, a cover of silence built for hunting. For a tarsier, a world sized precisely to its enormous eyes. Darkness, on this planet, was never really empty. It was simply operating on a different shift, with its own economy, its own romances, its own dangers, running in parallel to the one governed by daylight. And whether the hour is day or night, whether the setting is desert, reef, forest, or open ocean, every creature in this film has been answering some version of the very same question, over and over, in a different accent each time. Return, for a moment, to where this journey began, a singlewood frog, frozen solid beneath a fallen log, its heart stopped, its blood turned briefly to ice, waiting out a season it had no ability to escape. That frog is not separate from anything you've seen since. It shares its strategy for defeating winter with the ice fish drifting through Antarctic water on nearly colorless blood. It shares its patience with a tardigrade curled into a near-lifeless husk, waiting years for a single drop of water. It shares its ultimate purpose, however briefly its own life burns, with the octopus mother fading in her den, and the emperor penguin standing motionless through 100 days of Antarctic dark, and the exhausted godwit finally touching down in Tasmania after 11 days over open ocean. Each one of them is a single answer. But zoom out, even slightly, and something larger comes into focus. A single wood frog matters to its pond, providing food for the herons and snakes that hunt it, and controlling the insect populations it feeds on in turn. A single keystone predator, like a wolf reintroduced to a landscape it once vanished from, can alter the very course of a river, changing where deer choose to graze, allowing forests to regrow along the banks, stabilizing soil that had been eroding for decades. Off the Pacific coast, the disappearance of sea otters from a stretch of kelp forest has been shown, repeatedly, to trigger the same kind of collapse from an entirely different direction. Otters control local populations of sea urchins, and without that control, urchins graze kelp forests down to bare rock within a few short years, taking with them the fish, invertebrates, and other otters that depended on that kelp for shelter and food. Return the otters, and in time, the kelp forest can return as well. A single species, missing or restored, and an entire underwater forest hangs in the balance. Zoom out again, and entire ecosystems reveal themselves as characters in a story far larger than any one of them could tell alone. A rainforest canopy doesn't just host wildlife, it helps generate the rainfall that sustains agriculture a continent away. A coral reef doesn't just shelter fish, it buffers entire coastlines from the force of the storms battering them. A forest connected root to root by fungal threads doesn't just grow trees, it may be redistributing resources with a subtlety we're only beginning to measure. None of this is guaranteed to last. Earth's history includes 5 mass extinctions violent enough to erase the majority of species alive at the time, and long before any of them, this planet's story continued regardless, because life, as a whole, has never once been the fragile part of this equation. Individual species are fragile. Individual chains of dependency, a single keystone species, a single migratory route, a single narrow window of tolerable temperature, are fragile. Life itself, as a process, has proven itself almost absurdly persistent. Zoom out once more, and you arrive at the full, staggering scale of the planet itself, one single, interconnected system of weather, ocean current, forest, and reef, in which wind patterns above the Sahara Desert help fertilize the Amazon rainforest with dust carried thousands of kilometers across an ocean, and the health of krill in the Southern Ocean quietly determines how many whales will sing, migrate, and feed in the decades to come. Zoom out one final time, and life itself becomes the subject, an unbroken chain stretching back roughly 4 billion years, from the first simple cell in a warm ancient ocean, through ice ages, mass extinctions, and asteroid impacts violent enough to end nearly everything alive at the time, all the way forward to a frozen frog thawing in a puddle of spring meltwater, this year, on this planet, completely unaware of how many failures had to happen before its own particular success became possible. And somewhere inside that same staggering chain, stands us. Humanity did not arrive to observe this story from the outside, the way an audience watches a screen. We are a chapter within it, a species that inherited the same fundamental biology as every creature in this film, the same drive to survive, the same instinct to protect our children, the same capacity, still not fully understood, for something that might reasonably be called feeling. We are also, uniquely among every species we've encountered tonight, the only one capable of understanding this story well enough to change how it ends. We can choose to protect the wetlands a single beaver family spent generations building. We can choose to leave enough undisturbed reef for a clownfish and an anemone to keep negotiating their small, perfect truce. We can choose to give a colossal squid's ocean, and a tardigrade's desert, and a firefly's field at dusk, enough room to keep existing on their own terms. We can choose to leave the deep ocean's darkest, least explored habitats intact long enough to actually discover what's living inside them, rather than losing species we never had the chance to name. Or we can choose not to. That choice, unlike almost everything else in this film, belongs entirely to us. Every creature you've witnessed across the last 90 minutes has spent millions of years refining a single, precise answer to an impossible question: how do you keep existing, on a planet that never stops testing whether you deserve to? The wood frog answered with sugar, and time, and the willingness to let its own heart stop rather than lose the war against winter entirely. The elephant answered with a language pitched below the reach of human hearing. The octopus mother answered with the last of her own body, given completely, so that 100,000 small lives might have a chance to begin. And somewhere, right now, in a forest, a reef, or a trench we have still never seen with our own eyes, some other creature is quietly finishing an answer of its own, one that no camera has filmed yet, and no scientist has explained yet, and that may be stranger, and more beautiful, than anything captured in this film. The story was never really about the animals. It was about what it costs, and what it means, to still be here, on this improbable, overcrowded, endlessly inventive planet, after 4 billion years of almost not making it at all. And for one more day, at least, life found a way to answer that question again. So did you.